Welcome to Mac TV with Professor V. In this video, we're going to learn about plane curves and parametric equations. This is video lecture for section 10.7 Precalculus. Definition to kick things off. Let x equal f of t, so x is a function of t, and y equals g of t. Y is another function of t, where f and g are two functions whose common domain is some interval I. The collection of points defined by ordered pair x comma y, x coordinate is equal to f of t, and the y coordinate is equal to g of t, is called a plane curve. And the two equations, x equals f of t and y equals g of t, where t is in the interval I, are called parametric equations of the curve. And the variable t is called a parameter. So just some things to get straight. Even though there's three variables going on, t, x, and y, we're still only graphing in a two-dimensional coordinate system. So you do not plot t. T, the parameter, varies. It's always increasing. And then you trace out the plane curve defined by the parametric equations, which give you the points x and y as t changes. So here's an example. Notice we're in two space xy coordinate system, okay? And t varies from a all the way to b. So that's where we say t is in this interval I. So for this particular example right here, we'll say the interval I is from a to b. Notice a and b are not plotted in the xy plane. No. T starts at a. You get your first ordered pair xy by figuring out what f of a and g of a are. And then the last value that you're going to plug in for t is b. And then you get another ordered pair, f of b, g of b. And these are all the values that x and y take on along the way. Notice there's a direction of motion which we indicate with these little arrows along the curve. And it's no surprise that we use t for the parameter a lot of the time because t will often represent time. So as time increases, you can follow the motion of a particle or an object in a two-dimensional coordinate system. And then if you go on to study more calculus and you start working in 3 dimensions, then your parametric equations will have one more component. I know it gets spicy. Later on, you'll have z equals h of t, etc. So you're not limited to two space, okay? Just keep in mind, you don't plot the parameter. You just use the parameter to generate the coordinates x and y. And parameter is always increasing, okay? Good, here we go. So let's look at some examples. Graph the curve whose parametric equations are given and show its orientation. So that means use little arrows to mark along the curve so you know which way it's being traced out. And then find the rectangular equation of the curve. We'll talk about what that means in a second. So I'm looking at the parametric equations here. We have x equals 2t minus 4, y equals 4t squared, and then they're telling me the parameter t can take on any real number value. So the interval I is just all real numbers. Remember we said I on this example was just from a to b. Well, look at us. We can just run free. Anything from negative infinity to infinity is good to go. So let's make a table and we'll plug in a few values. And if we feel like it's enough, then we can just plot those. If we need more, we can always add to the table, okay? So t, x, which is 2t minus 4, and y, which is 4t squared, okay? So we're going to be plugging in various values of t. Let me scoot this over. Where to start? I mean, I usually do from -3 to +3 if I'm not given any guidelines like we were here. And then we can just play around with it, observe, see if we want to add more. Okay, it's all up to you. So -3, -2, -1, 0, 1, 2, 3. Sound good? All right. So if t is -3, x is going to be 2 times -3 minus 4, that's -10. Let's just keep doing all the x's so that we can get in a groove. 2 times -2 minus 4, that's -8. 2 times -1 minus 4, that's -6. And you can see these are all increasing by 2. You guys, that should be no surprise, right? Think of it, it's basically giving you a linear equation here. -4, -2, 0, 2. Okay, and then y equals 4t squared. So when I square -3, it's going to become +9. And then times 4, that's 36. -2 squared is 4 times 4, 16. -1 squared times 4, 4, 0. And then these repeat, 4, 16, 36. All right, so I want you guys to write down all of the ordered pairs before we start. So the first one would be -10, 36. This is the x coordinate, this is the y coordinate. Notice that ordered pair came from substituting t equals -3 into the parametric equations. Do you plot -3 anywhere? No. Okay, just the x and the y. Next ordered pair, -8, 16, -6, 4, -4, 0, -2, 4, 0, 16, and 2, 36. All right, good. So I'm looking at things. Let me darken the axes. It's a little hard to see. Okay, here's the y-axis. Here's the x-axis. It looks like x values are going from -10 to +2 so far. Okay, 1, 2, 3, 4. That's -5. 6, 7, 8, 9, 10. Ooh, we barely made it. 1, 2. You could scale differently, you know, if you need to. And then the y values, ooh, we have to go all the way up to 36. So let's just count by 5s on the y-axis. So this will be 10, 20, 30, 40. All right? All right, so let's start plotting the points. We have -10, 36, so that will be right around here. -8, 16, -6, 4, -4, 0, -2, 4, 0, 16, and then 2, 36. All right, it's pretty clear to me. This is looking like a nice parabola. And I'm gonna add arrows on the ends to show that it keeps going, right? Our parameter varies from -infinity to infinity, but we also need to include the direction of motion. So remember, we traced out the curve in this direction, down and then back up. That's important. All right. Now the second part of the problem asked us to find the rectangular equation of the curve. Other way that you might see this asked, depending on your textbook, it might say eliminate the parameter. So basically what they want you to do is work with the parametric equations and get rid of t so that you just have a regular Cartesian or rectangular equation that only uses x and y, okay? We need a little more space though, I think, right? We don't want to be squished. You guys never squish that extra problem in the margin of your paper. That's usually when students make a mistake. It's like if your brain doesn't have room to think properly, even on the paper, it doesn't cooperate. Okay, so the parametric equations were x equals 2t minus 4 and y equals 4t squared. In this scenario, it's usually easier to solve for t in one of the equations and then substitute that into the other one. I'm going to solve for t in this equation because I can do so pretty easily. I don't want to deal with the plus or minus square root from here. You see what I mean? So we have x plus 4 equals 2t. So t equals x plus 4 over 2. And then now I'm going to substitute that in for t there. So y equals 4 times x plus 4 over 2 squared. And then we can clean this up because I can distribute that exponent and write it as x plus 4 squared over 2 squared, which is 4, so this cancels. And then we just get y equals x plus 4 squared. And you guys, you studied parabolas a little while ago, but hopefully you haven't forgotten everything. This is the equation of a parabola whose vertex is at -4, 0, opens upward. Check. Is that what we graphed? Why, it is. Look at us. So professional. Okay. If you want to eliminate the parameter first so you know what sort of graph you're supposed to get, you can always do that too. All right. Let's look at another example, this time involving trigonometric functions. This is pretty common. We have x equals 2 cosine t, y equals 3 sine t, and t ranges from 0 to pi. Okay. So let's again make a table. This time I'm only plugging in values between 0 and pi. And let's just be nice to ourselves for now. And I'm just going to plug in values of t for which sine and cosine are going to be integers. So I'm just going to plug in 0, pi over 2, and pi. And then if this isn't enough, we can add to it, okay? So 2 times cosine of 0, that's 2. 2 times cosine of pi over 2, that's 0. And 2 times cosine of pi, -2. All right. 3 times sine of 0, 0. 3 times sine of pi over 2, 3. 3 times sine of pi, 0. So here are our ordered pairs. 2, 0, 0, 3, -2, 0. Okay. Is that enough? Well, it's enough for me, but maybe you need a little bit more to see what sort of shape is getting traced out, because right now all you have are a few points, 2, 3, -2. So right now all we have are 2, 0, 0, 3, -2, 0. I'm going to actually eliminate the parameter now with you guys, and then we won't have to add any more points to the table. Life will work out nicely. So we have x equals 2 cosine t and y equals 3 sine t. Typically, when you're working with trigonometric functions, you're going to want to use your Pythagorean identities to eliminate the parameter. What do I mean? I'll show you. If you were to get cosine t by itself, you would have to divide by 2. So x over 2 is equal to cosine t, right? And then similarly, y divided by 3 is equal to sine of t. And we all remember, since we just did trig a hot second ago, cosine squared t plus sine squared t equals 1. So I can just replace cosine squared t with x over 2 squared. Sine squared t I can replace with y over 3 squared. And this is all equal to 1. So now I've eliminated the parameter. I've already done the second half of the problem, but I can recognize, since we all just studied conics, that this is the equation of an ellipse. Centered at the origin, major axis length 6, A is 3, minor axis length 4, B is 2. So I don't need to plot any more points. I know this is going to be an ellipse, but it's only the upper half because t is restricted between 0 and pi. So let's draw it nicely. We're going this away. I'm indicating the direction of motion and back down. And then no arrows on the endpoints, right? Because t is between 0 and pi only. It does not keep going round and around. Okay? Good, that's it. Now, sometimes you're going to need to come up with parametric equations of your own. especially later on when you're in calculus. So find two different pairs of parametric equations for each rectangular equation. So they want us to come up with a possible combo for x and y that would give us this rectangular equations graph. Okay, so one obvious choice is, it's kind of boring, but it works great. You just let x equal t, and you're just swapping out variables. Then y would be negative 2t squared plus 1. In this case, the parameter t could be any real number, right? And you would generate all possible points. Okay. Another option is you could let, and you can play around with it, there's more than one possibility. You could let t equal x squared, and then y would equal negative 2t plus 1. Now this would give you back the same rectangular equation, but it would not yield the same graph, because notice t, since it's equal to x squared, is never going to be negative. So t is always going to be greater than or equal to 0. And so you wouldn't get the full parabola's graph because you wouldn't be plugging in any of the negative values for x. Okay, you'd only get the right half of the graph. So just be careful. Depending on the circumstance, you may prefer one set of parametric equations over the other, but just know that some of them come with inherent domain restrictions, so the graph will be different of the plane curve. All right. Next example, we're still finding equations. This time, they want us to find parametric equations for an object that moves along the ellipse, x squared over 4 plus y squared over 9 equals 1. But it needs to begin at 0, 3, go counterclockwise, and requires 1 second for a complete revolution. We are going to worry about that part at the end. Okay, let's not stress ourselves out. Let's first think back to how we graph an ellipse using parametric equations. It's no coincidence we just did this exact curve earlier. X squared over 4 plus y squared over 9 equals 1. That's this guy right here. X squared over 4 plus y squared over 9 equals 1. And we saw that these were the parametric equations. X equals 2 cosine t, y equals 3 sine t. But remember, when t was 0 here, we started at 2, 0. We started here. And that's not what we're asked to do for this example. They want us to start at 0, 3. Oh my goodness. Okay, so things are getting a little spicy. They want us to start here, and they want the graph to be traced out counterclockwise. So basically, you want x to be 0 first and y to be 3 first. So let's just take a guess. Just take a guess. Try x equals 2 sine theta and y equals 3 cosine theta. You see how I switched them? That way x would be 0 when theta is 0, and y would be 3 when theta is 0. So let's see if this works. Theta x, y, and they want 1 complete revolution. Okay. So I just want to check, is the direction going the right way? So we'll put 0, pi over 2, and pi, and see what happens. So if theta is 0, sine of 0 is 0, and then at pi over 2, sine is 1, so this would be 2, and at pi, sine is 0, so this would be 0. And then the y-coordinates, cosine of 0 is 1, so 3 times that is 3. Cosine of pi over 2, this is 0, and then cosine of pi is -1, so this would be -3. So right now we have 0, 3, which is good, then 2, 0, then 0, -3. So 0, 3, 2, 0, 0, -3. So the curve is going this way. Is that what we want? Is that counterclockwise? No, it's not, okay? So what to do? Well, usually you don't want to switch back the sine and the cosine. We are happy that this is 0, 3. So we're just going to need to add a negative somewhere to reverse the direction of motion. And let me put it in front of sine theta and see if that works. Okay, so if I change x to be negative 2 sine theta, we'll still start at 0, 3, right? I don't want to put the negative here because then that would make that 0, negative 3. I don't want that. I still want to start at 0, 3. So let's put the negative in front of 2 sine theta. So then this will be negative, right? And then let's see if that works. So this is my new addition. So then this will be negative. So we'll go from 0, 3 to negative 2, 0 to 0, negative 3. Yes, now we are happy. This way, we will pretend this didn't happen. Okay. Now, how long will it take for one complete revolution? Well, theta will have to range all the way from 0 to 2 pi, right? And then when we're back at 2 pi, then this will be 0 and this will be 3 again. So let's think about what they're asking us to do at the very end. They want 1 second for a complete revolution. So right now theta ranges between 2 pi and 0. That's 1 complete revolution. And what we want is for our parameter to represent time and for that to range between 0 and 1, being measured in seconds. Okay? So how do I need to adjust the limits on theta so that they become 0 and 1? Well, I'm already happy with the lower limit. I just wish that that 2 pi was a 1. So I'm going to divide everything by 2 pi, divide by 2 pi, divide by 2 pi. And then now I have that 0 is less than or equal to theta over 2 pi is less than or equal to 1. So what I'm going to do is say let t equal theta over 2 pi. And so if I go back to my parametric equations here that were in terms of theta, I'm going to solve for theta and replace it so that now I'm using parameter t. So theta equals 2 pi times t. And now my parametric equations are going to be x equals negative 2 times sine of 2 pi t, y equals 3 times cosine of 2 pi t, and t varies between 0 and 1. Okay, so t is measuring time in seconds, and we've completed the problem. Okay, so just to recap, originally I wrote parametric equations using theta as my parameter, just because that's very natural when you're tracing out some sort of ellipse, right, in a circular fashion. We ensured that the direction of motion was counterclockwise, and we started at 0, 3, which was a little tricky. Then we had to change our parameter so that we used t representing seconds, and the limits needed to be from 0 to 1 instead of 0 to 2 pi per the directions, okay? And then you just adjust the interval accordingly. That's probably the trickiest thing you're going to have to do in this section. Last idea, if you've already taken some physics, then you've probably seen this already. It has to deal with projectile motion. So when an object is propelled upward at an inclination theta to the horizontal with initial speed v naught, that little subscript 0 means initial, so initial velocity, the resulting motion is called projectile motion. In calculus, it's shown that the parametric equations of the path of such a projectile fired at an inclination theta to the horizontal with initial speed v naught from a height h above the horizontal are as follows. So x is equal to v naught cosine theta times t. Y equals negative 1/2 gt squared plus v naught sine theta times t plus h. I'll break this down for you. This g here is acceleration due to gravity. So on the earth, that's 9.8 meters per second squared if we're in the metric system. And then h is that initial height where you're standing. So imagine you're here Hey, what's up? I'm going to throw a baseball. Boom, this way. Okay, and its trajectory, its motion is modeled by these two parametric equations, x and y. They take into account the angle at which you threw that baseball, how quickly you threw it, the initial speed, the height you were at where you were standing, and then t is the parameter. So as t varies, you can trace out the motion of the particle, okay? If you have an old MS-DOS computer, you probably don't, you're also young. There was this game Gorilla where you would chuck bananas and it was very fun. And as a child, I played adjusting the initial velocity and theta so that I could hit the target while chucking bananas. Little did I know it was educational. Okay, so let's look at an example. Suppose that Carla hits a golf ball off a cliff 300 meters high with an initial speed of 40 meters per second at an angle of 45 degrees to the horizontal on the moon. Ooh, gravity on the moon is 1/6 of that on Earth. Okay, before we get into it, let's just start labeling everybody. So Carla's on a cliff 300 meters high. She is brave, Carla, you go. Okay, so that's H. Initial speed of 40 meters per second, that's V naught. At an angle of 45 degrees, there's my theta. And then they told us we're on the moon, so gravity is only 1/6 of that on the Earth. So what we're gonna use is 1/6 times G, okay? So right here, instead of using regular G, we're gonna have 1/6 of G. So part A asks us to find the parametric equations that model the position of the ball as a function of time. So we're just finding x and y. So x is going to equal V naught, that was 40, cosine 45 degrees times t. I don't know how your professor feels about rounding, so I'm just not going to round and keep things really pure and exact, and then if they let you, go for it. So cosine 45 we know is rad 2 over 2. So x equals 40 rad 2 over 2 times t. So we have x equals 20 rad 2 times t. Okay? If they let you round, then you can round. I'm not. Y equals negative 1/2. And then remember, instead of g, we're using 1/6 of g. So 1/6 of 9.8. I don't want to mix decimals and fractions. 9.8, I know it's rounded, but I'll just write it as 98 over 10 for now, and then we can reduce, okay? T squared plus, we'll have V naught 40 sine 45 times t plus, what was H? 300. Okay, and then if you clean it up, you'll get y equals, a lot of stuff will cancel here. So we'll end up with, I can divide this 2 into 98. That's going to give me 49. And then I don't think anything else reduces. 49 is just 7 times 7, and 6 and 10 don't go into that. So this is going to be negative 49 over 60 t squared plus 20 rad 2t plus 300. Okay, so those are the parametric equations that model the position of the ball as a function of time. And we know t is going to start at 0. That's the initial position. Okay, second part of the problem asks how long is the ball in the air? So they want to know what's the time that the ball spends in the air. So you want to know at what time it hits the ground. Well, to figure out the time at which it hits the ground, you need to set y equal to 0. When the vertical distance is 0, then the ball has hit the ground. So set y equal to 0 and solve. So we're going to work with this parametric equation here. And I'm going to multiply everything by -1 so that my leading term is positive. So we're going to have 49 over 60 t squared minus 20 rad 2t minus 300 equals 0. This is quadratic, so we can use the quadratic formula. I'm not even going to try to factor this. So t equals opposite of b plus or minus square root b squared. So 20 squared is 400. Rad 2 squared is 2. So 400 times 2, that's 800. Minus 4ac all over 2a. And yes, I busted out the calculator to figure this out, and you get two values. So I'll just round to 2 decimal places because otherwise this would be a nightmare. 43.15 and negative 8.51. So we're not going to use the negative value for t. We can't go back in time just yet. So our answer is 43.15 seconds. You guys, it should make sense that one of the answers came out negative. Look why. Look why. We wanted to know when the ball hit the ground, right? You can see like this is a parabola. If you follow the symmetry, it also hits the ground when time is negative back here. Oh my goodness. Okay. Next part, determine the horizontal distance the ball travels. So what it's asking is, what is this distance here? Okay, how far does the ball travel in the x direction? So basically we want to know what is x when the ball hits the ground. Okay, so I know the time at which the ball hits the ground, it was 43.15 seconds. So I'm just going to plug that in to the parametric equation that gives me x. So x equals 20 rad 2t. The horizontal distance is going to be approximately 20 rad 2 times 43.15. So 1220.40 meters. And always check with your instructor how they want you to round if you need to follow sig figs or a certain number of decimal places or whatever. Just do what they say. Last part of the problem asks, when is the ball at its maximum height? And then determine the maximum height of the ball. Okay, which of our parametric equations tells us about the height or the vertical position of the ball? The equation that gives me the y coordinate, right? That tells me how high it's going, up and down. Y goes vertically. So let's look at that parametric equation in more detail. Y equals negative 49 over 60 t squared plus 20 rad 2t plus 300. All right, think back when we were just graphing parabolas early in the semester. This is a quadratic equation, so I know its graph is going to be a parabola. And since this leading coefficient is negative, it's a parabola that opens downward. And if we're trying to find the maximum, all I'm after in the case with a parabola is finding out where its vertex is, okay? And they want us to answer the question, when is the ball at its max height? So find the t that gives us the vertex, and then what is the max height? So give that y value. Well, do you remember a quick way to find the vertex of a parabola? We use, to find h, or in this case, I'm going to call it t. T equals opposite of b over 2a. Same a and b like from the quadratic formula. So opposite of b is going to be negative 20 rad 2 over 2 times negative 49 over 60. And then if you round this, it's approximately 17.32 seconds. I only rounded to write my final answer. If you're especially paranoid, leave that number in your calculator. And then when you're figuring out the max height, you can just use that second answer key. So y of 17.32 is going to be negative 49 over 60 times 17.32 squared plus 20 rad 2 times 17.32 plus 300. And this is about 544.90 meters. So what I mean is, don't clear this number. And then every time you would normally type it in to figure out this value here, most calculators have a key that says answer, pulling up the previous entry that was in the calculator. And then that way you don't have so much rounding error, okay? It'll be more crucial later on, but I just want you guys getting comfortable with your technology now and trying to round at the last step whenever possible. Okay, so that concludes the lesson. Hope you found it helpful. Give it a thumbs up. Subscribe if you haven't already, and share this video with whoever else you think would like it. And stay tuned. We have more sequences and series coming up next, believe it or not. Yes, we do.